Welcome to the July 2016 Energy Lunch. It's July in Western Washington. I didn't have to wear a wool sweater this morning. So today we have Michael Burr from the Microgrid Institute in Minnesota. But first I'd like to thank our sponsors, Bob Grimm, Alaska Power and Telephone, Steve Tucker from the Port Townsend, Robert Urish from the Sunshine Propane, I don't see him here, Letitia Huber of Hooper's Inn, and finally Andy Cochran from Power Trip Energy. Michael's talk today is entitled Rethinking Public Power, Microgrids and District Energy Development. Michael, as I said, came to us from the Microgrid Institute based in Little Falls, Minnesota. He is the founder of the Microgrid Institute, started in 2012 to help chart pathways for adoption of distributed energy resources and to help communities and organizations to achieve greater energy resilience and self-reliance. He'll discuss how market forces are driving adoption of distributed energy resources, DERs, and microgrids, how microgrid technologies support local energy, resilience, and economic development, regulatory and financial barriers to microgrid development, and he'll share some experiences from the front lines of microgrid development in New York and Maryland, Montgomery County. So please welcome Mr. Michael Burr.
Thank you, Sonia. I really appreciate it. All right. I'm really glad to be here today. It's a great topic, obviously something that's close to my heart and I've been working on for a number of years. And I've really been gratified to talk with some of the folks in the area here and learn all the interesting things that you're working on. You've got some big goals and interests, and I'm hopeful that my comments today might help shed a little bit of light on some aspects of that. But there's a lot of different options and possibilities, so I'll be very keenly interested to see where it goes from here in the Olympic Peninsula generally, actually. The title of my talk, I evolved it and simplified it a little bit. It seems to me that the issues that are of interest here in Jefferson County are also of interest in to other folks across the Olympic Peninsula. So I broadened the subject out and simplified it a bit. But anyway, the point is, what are our pathways to energy resilience? And I can't say that I've spent huge amounts of time looking at the challenges here, but I've spent a little time, and I'll try to bring a little bit of insight into that based on some of the work that we've been doing at Microgrid Institute. So we'll start out just kind of to make sure everybody's on the same page with regard to what the subject is, and what microgrids are, and what's driving them. We'll talk about some of the trajectory and trends that's leading toward development and adoption of microgrid technologies. And then we'll talk about some of the specific challenges here that factor in when we're thinking about microgrids. And then finally we'll talk about how Microgrid Institute goes about helping communities like Port Townsend and Jefferson County to try and work through some of these issues. So, first of all, I just wanted to mention also I brought a bit of collateral and forgot to put it out till everybody had already sat down. There's a card here with a diagram, kind of simplification of how microgrids work, and a little bit of information on the back, just for your interest if you want to grab one of those. Also, I put my business card out as well. Basically, though, a microgrid is a system that's all about balance. It's about balancing energy supply against demand, or vice versa, keeping energy system in balance. The macro grid, the utility grid, does that on a very large scale using really huge power plants that have a lot of reserve capacity, known as reactive power, to respond quickly to a short-term increase in load on the system. In a microgrid, you've got to come up with a solution that can do the same thing. And that gets increasingly difficult the smaller the microgrid is, and the more you're relying on energy supplies that may not be able to react quickly. So that's really what a microgrid is about. It's about a control system and a set of resources that are capable of maintaining a balance in a small area when the grid, the utility grid, isn't available for whatever reason in an outage scenario. I wanted to mention too, sometimes people ask what's a microgrid, and we get into a discussion about a definition of a microgrid and trying to really narrow it down. And I like to say, sort of half jokingly, a microgrid's whatever you want it to be. And that's only half a joke, because really it is about serving the customer's individual specific needs as opposed to the generic needs of all customers on the system. The utility industry is about sort of plain vanilla approach, or Black Princess telephone approach, whereas a microgrid is a customized, engineered solution for a specific set of customer needs. That really differentiates it from a backup power system or from the utility grid. We'll get into some of the details in a bit here, but I wanted to just really quickly go through how microgrid really works to achieve balance. And not every microgrid works the same way, but they all do something similar to what I'm going to walk through here. So if you have a supply and a load, and you're hooked up to the utility grid, and for some reason the grid goes away, an outage, for example, in most cases, the microgrid has to react to that. And so the way that it reacts to that, first, you see that orange line there, it separates, it isolates itself from the utility grid so that it's not accidentally feeding power up onto power lines that line workers anticipate to be dead. In other words, if you're out there trying to fix the line, you think the lines are dead, and somebody has a generator feeding power onto the line, you're going to get electrocuted. So a microgrid automatically isolates to avoid that problem. It's a safety issue, and also protecting equipment on the utilities distribution system. So that's the first thing it does. The second thing it does is it has to react to an imbalance, because if it lost the grid, that means it doesn't have enough supply to meet the load that was being served at the time that the grid went down. So what does it do? Well, it may be able to shed some load. So you can see the optimal load dropping off. The microgrid controller will shed the load that's optional, that doesn't absolutely have to be served, and it will. You also see the storage amount on the left there is real small before the grid went down. After it goes down, it'll suddenly discharge batteries to try and fill in that gap. But you see the total load now it's less than what it was before, and we want to maintain service for as many of the customers, as much of the loads as possible. So it takes some additional steps to fire up additional generation resources and to send signals to modulate loads to limit the amount of discretionary loads that are being used at that given time. Now that's a really oversimplified way of looking at it, but that I hope in a nutshell explains how microgrid works. It needs to maintain system balance, and it can do that either by increasing supply or decreasing load, or both. And the most advanced microgrids do both. I include storage in this example. Not all microgrids have storage. Some of them experience an outage. So during this period when the grid goes down, there's a blackout on the grid. And there will be a period of time where the system is going to fire up its generation resources in order to get it back online. So not all microgrids operate exactly like this, but this is the general idea. So there are multiple different types of microgrids, and as I said, it's whatever you want it to be, and so that literally means every microgrid is pretty unique. But they can be divided into a few types. So typically people think of a microgrid as being a campus scale system. So university campus, or a government campus, or a prison, or a military base, something like that, that's a single owner. And then also sometimes we talk about nanogrids. They're just small microgrids, basically. Typically people think of a nanogrid as being a single building or a single facility. And sometimes, you can mess around with that definition as well. But the point is, it's a very small microgrid. And in both cases, really most of those are meant for mission-critical energy supplies for something like a prison, for example, or a university or a hospital, where there are critical components that you need to keep powered consistently. Then there are island microgrids, or remote microgrids, like we see in Alaska, or on islands out in the ocean in the Pacific. And those are cases they're not connected to any grid at all. But we think of them as a microgrid because it's small, and because that means the same challenges are seen as are seen in a system that's connected to the grid. It's small, and therefore it has to have a solution that can actively keep the thing in balance. Some microgrids are just way oversized in terms of supply, and so it doesn't have to really do a lot of active balancing. But what we're seeing today is an effort to keep things as efficient as possible and as cost effective as possible, and that means you need a smart system. Rather than just overbuilding your generation, you want a system that can really work to keep things balanced. Finally, and the most advanced, is the community microgrid. And this is really something new, frankly. There aren't very many of them in operation in the United States. There are really just a few that I would consider community microgrids, but it's a very hot area of development in many locations, specifically because communities are seeing a need to increase their resilience against a wide variety of threats against, against their critical assets. That's first responders, hospitals, and even things like grocery stores, gas stations that become really critical in a long-term outage. If you're out of power for a few hours, well, you probably don't need to go to the grocery store. But if you're out of power for a day or 2 days, you probably do, and maybe you need to get to the pharmacy. Those types of things become critical as an outage gets longer and longer. The other thing is that communities see a need to make it possible for their citizens to shelter in place. So if there's a hurricane or an earthquake or something that happens that creates widespread disruption, people don't have to evacuate. They can stay in their homes. They may not have power in their home, but they know that the grocery store is running and they can get ice and food, the hospital's running, they can get around and they can stay there instead of having to evacuate. And that can really help to make it possible to recover more readily from a major situation. Two community microgrids leap to mind for me. There are others, and there are some outside the U.S. But in the United States, Borrego Springs in California, in San Diego Gas and Electric's territory, there is a microgrid there. It's not serving all of Borrego Springs, but it's an example that's pretty instructive for us here because it's at the end of a long transmission line that has historically had a lot of outage problems, and they put in place a microgrid based on a substation that serves a community area that uses a lot of solar power. It's based largely on photovoltaics and I believe diesel backup, or I'm not really sure, to be honest, off the top of my head. But Borrego Springs is one example, and some of our team members were involved with that project, actually designing it. And then another one is called Co-op City. It's in the Bronx in New York. That's a completely different kind of microgrid, more like what I was saying, where they oversize the generation. That's a case of a power plant with a microgrid attached to it. I think of it that way. It's a cooperative housing development with a number of high-rise condominiums, as well as some commercial buildings, and it's all served by a large natural gas-fired power plant. So I call it a community microgrid because it's multiple buildings all served by one system that maintains the balance. But it has an easy time maintaining balance because it has so much generation capacity. They sort of, from a business model perspective, that's almost the retail sales to the microgrid is icing on the cake. Most of the power is just sold on the wholesale market in the New York ISO. Those are two examples. There's others, but they're really smaller scale demonstration projects. And there's a lot more that are in development. Dozens and dozens of them, but none of them, to my knowledge, have really started construction at this point. And there may be a few other examples we can point to, but those are the best ones, I think. So I mentioned the idea of balance before from an operational perspective, but you also have to think about a microgrid as a holistic, integrated energy system. And that means it needs to maintain balance in many different ways, including economics, including legal and regulatory issues. I'm speaking metaphorically here, but the fact is it's very difficult to build microgrids for a multitude of reasons, not just technical. And actually the technical reasons are the easiest to solve in a way. We know how to solve them. It's the economic and legal and regulatory issues that are trickier to solve. And we'll touch on some of those issues a bit later, but I wanted to point this slide out because when we look at assessing a microgrid, we always have to look at it from a perspective of operations, but also an integrated system that has many different facets and aspects that need careful attention in order for a microgrid to be successful. The San Diego Gas and Electric example, the Borrego Springs one, that's a demonstration project by a utility. They decided to make the investment to prove out how the technology can work. So in a way, that example shows that we haven't figured out how to build microgrids, because if the only way they can get built is if a utility just says, okay, let's do this to do kind of a science project, which was a necessary science project, but nevertheless, it wasn't a free market, private enterprise, commercial kind of endeavor. We have some work to do. And that's really what Microgrid Institute is focused on pretty heavily, is to try to figure out how to get this done. I wanted to talk a bit about the trajectory of microgrids. One thing to keep in mind is that some people look at microgrids and think, oh, it's kind of a flash in the pan, or it's a fad, because it's been a really hot topic for the last few years. And it is very hot now. But I caution people to not think of it that way, because the fact is microgrids are part of a trajectory of trends that's been happening since the 1980s, or even earlier, depending on how you look at it and how far you want to take the discussion. But what it really boils down to is that we've been seeing over a course of decades a growing need for solutions that are more flexible, more capable of meeting local energy requirements, and to meet a set of needs that the major, the centralized utility system hasn't been meeting. That's because it wasn't designed to meet them. But these needs are somewhat new, and they're evolving and developing, and there's a whole variety of trends that are emerging to meet those changing needs. Microgrids are one of those things. I don't expect anybody to be able to read this, but it goes to the point that this trajectory is on many fronts, and I guess I can't zoom in on it for you, but regulatory, from a perspective of regulation, technology, market structure, transactional contracting structures, all of these things have been evolving all in the same direction over a course of decades. And that same direction is toward more disintermediation of the market. So what that basically boils down to is that instead of it simply being a centralized utility market where the utility owns the territory and sells you power on a plain vanilla basis, now there are new solutions that kind of get in between the customer and the utility and offer different alternatives. And that trajectory has been happening on every front, frankly. So the point I'm making is that it's not dependent on any one thing. Microgrids are evolving and emerging, and they likely will continue to emerge. And it's not all dependent on the emergence or the improvement in storage technology, for example. A lot of times people will say, well, if you don't have storage, a microgrid's not going to work, so we're going to hit a plateau with storage technology, and that's going to be the end of the story for microgrids. I totally don't accept that, because it's not all about storage. It's about many different things, all of which are continuing to evolve, become more cost-effective and more capable. So that's, I guess, my soapbox point for the day, one of them anyway. I wanted to talk about a couple of specific projects that we've been working on and some of the lessons we've been learning out of that. So we have 3 active community microgrid projects underway right now. They're all fairly early stage. We haven't put any steel in the ground yet, or installed any equipment. One of them is this one, the Only Town Center microgrid. It's funded by the U.S. Department of Energy as a design and testing project. So what we've been doing is designing and modeling a microgrid that would serve a 1 square mile area of downtown Olney, Maryland, which is about 20 miles north of Washington, D.C. So it's in a very heavily populated corridor, near the national capital. And in this area, in 1 square mile, there's a major hospital, some public shelters, police station, grocery stores, a lot of things that are really considered vital to a community. And actually, for that reason, the Montgomery County, which is the administrative agency here, only is an unincorporated community, so it's really Montgomery County's authority. They designated this area as a town center. So it's already favored by the county as someplace that's important. So we took a very close look. And when I say we, it's a team including us as well as Schneider Electric, Green Energy Corp, and North Carolina State University, with Pepco as the utility partner. We took a close look at the distribution system in the Olney area and determined that in order to avoid overhead lines, which are vulnerable to storms, which is what the major threat they're trying to to prepare for. In order to avoid that threat, we need to avoid using overhead lines. And we looked at the distribution system and realized that either we had to bury a whole bunch of distribution lines, which is very expensive, especially in an urban area, or we had to sort of segregate the grid into multiple different zones and treat each as its own microgrid. And that's what the design actually does. Within this area there are, well, technically 6, but really 4 zones. I say technically 6 because there's 2 fire stations outside this area that have small nanogrid, would have small nanogrid applications. But within these 4 zones, each one would actually island separately from the grid or isolate itself from the grid and operate separately during a utility outage. But the resources within them would all be managed as a portfolio. So it would be treated as a single set of resources for economic and environmental purposes to bid demand into the market, for example, to produce a better economic outcome for the total system. We can go way deep into the weeds on how that works, but we don't have time. So I'm going to kind of move on, and if we need to, we can come back. But the point is that this is one of the first, and there are a few others that are in development out there. This is one of the first projects that's looking at a microgrid in this way as a package of multiple zones. And there's different words or terms that are evolving for it. Some people call them fractal microgrids because you have like one system and then it can separate into smaller iterations of itself. It's not a bad term, but it's a little deceiving because they're not all identical, of course. And that's what fractal means, is it's, the smaller you go, you have the identical design in a smaller and smaller package. That's not the case. Anyway, I'll move on. We're working on a couple of microgrids in New York. The state of New York created this thing called NY Prize. They funded feasibility studies for several dozen microgrids in the state, and they're all led by community, or at least in very close cooperation with communities. So towns and villages need to be the impetus behind it, and also they need to be performed in cooperation with the local utility. So we're working on 2 of these projects, and in both cases we have a town and a village as the administrative agency, as well as a number of other stakeholders, both public and private stakeholders that we've been working with to figure out what are the critical assets that need serving and what's a good way to serve them. What we came out with is a pretty unique design that takes the only model a step further. And I'm just going to focus on the New Paltz microgrid. Warwick is similar, but a different case. In New Paltz, we have, again, multiple zones, but it's 10 zones instead of just 4 or 6, depending on how you look at the only case. And they're spread out throughout the community. They're not clustered together. The reason for that is because the community's critical assets are not clustered together. And most communities don't have their critical assets all in the same place. So we have a elder care center up in the top right of this diagram. There's SUNY, the State University of New York, has a campus there with a large public shelter that would be helpful in an outage scenario. And a number of other assets, 2 grocery stores actually, a public housing development, and water systems, importantly. This microgrid actually would help to maintain water pressure and would also keep the wastewater treatment facility operating during a utility outage, all using small systems that are spread out throughout the community but operated as a single portfolio. So this goes against the traditional way of thinking about a microgrid. People have tended to think about a single campus. I mentioned that before. People always have thought about it as a single, in fact, my diagram, I'm not going to go back, this diagram shows a ring bus as if everything in the microgrid fits into that. This is an outdated diagram, even by the projects that we're working on, because it can be a basket of different assets in different locations. That's something I think worth thinking about here, because you have critical assets but not located very close together. And serving all of them with one system would be pretty tricky unless you take an approach like this. So a couple of things also to mention about the New Paltz project. I'm just going to jump ahead one slide and then I'll come back. One thing is that it's a public-private partnership. The proposal that the community is on board with is to be a public-private partnership that would include multiple public entities, the town and the village, theoretically the school district, maybe even SUNY, and maybe even the New York State Department of Environmental Conservation, because they have a regional headquarters in New Paltz that would be included in the microgrid. And so that brings some really important benefits. First and foremost is that a public-private partnership can access both public sources of funding and private sources of funding. There are some limitations, but it's more flexible than other structures. Another thing is that it makes sure that the system will focus on meeting the community's goals, because it's really driven by the community, by the local public stakeholders. But it also has private investors involved, and that's helpful because it makes it possible to raise funding and to move forward a project that may be more ambitious and add more value to the community than perhaps the public agencies would undertake on their own. So it's kind of a marriage of the best of both worlds, public and private. I wanted to mention the energy services model, which is actually mentioned down there in the bottom. I guess I should have flipped these two slides, because that segues into this one. The other thing that's interesting about the New Paltz microgrid is that it's not just a microgrid. The whole plan for this microgrid is first and foremost to design a system and to build resources that will meet the critical infrastructure or critical asset services requirements of the community. And then once you've designed that and have a plan for building that, then you can take the same resources, the human resources, the financial resources that you mobilized in order to do that, and you can bring that to bear to bring more green energy assets into the community. So basically the point is that the public-private partnership will be a business that provides resilience for critical services and then also offers green energy solutions for businesses and residents in the community. That can save money and improve the economic proposition of the public-private partnership, and therefore make it possible for the P3 to provide services that are, improving the resiliency of the community. The third tier in this multi-tiered model for New Paltz is community choice aggregation. And that's something that, as I understand it, is not available in Washington, but a number of states, including New York, have passed laws that allow an entire community to band together and say, as a community, we're going to use our buying power to negotiate a better deal out in the market. Since you have a PUD here in Port Townsend, that may not really be a factor, but in some cases it can help, and the microgrid actually can be the managing agency for that community choice aggregation construct. So the point is really that it really needs to be aimed at meeting a broad range of needs for the community, and what factors into that is the need for integrated energy planning. That's a point I should have tried to make earlier, I think, but I'm going to emphasize it now and talk about it a little bit later. One thing that we've run into is that when you're trying to design and develop a resilient energy microgrid, oftentimes you run into conflicts of interest and conflicts of other projects that are underway. One example in New Paltz is the school district entered an agreement to build a remote solar facility that will offset all of their electricity purchases. That's great for the school district, but what it does is it makes it impossible for them to participate in the microgrid because that solar asset is not going to be operational during a power outage. It's not integrated into the microgrid. In other words, if it were planned better, if it were part of an integrated plan, we could have used that asset, cited it and designed it and financed it in a way that could be part of the microgrid. But instead, they did it on their own, separately, and as a result, the school districts are going to have a hard time participating in this microgrid. At the end of the day, we may be able to come up with a special solution to serve one building as opposed to several buildings, which is what the original concept was. So it illustrates the need for integrated planning, basically. thinking about it from a big picture perspective and making sure that your strategic efforts are all in sync and not butting heads against each other. I'll move on and we can maybe hit some of those topics again, but that was about all I was going to say about those two projects. One thing I should note, because I guess it was promised I'd talk about regulation a bit. New York is embarking on has been for the last couple of years, has been embarking on a pretty ambitious effort called Reforming the Energy Vision, the REV program. And they're really taking an entirely new look at how electricity is generated and sold and delivered in the state of New York. That has been, a forward-thinking effort on their part. What comes out of that, I think a lot of states are going to be very keenly interested in learning from. How that's going to apply in a place like Washington, I don't know, because you have a really different kind of market. In New York, it's an unbundled market. Third parties have an opportunity to participate in a way that you don't see in states like Washington. So that's a point for further discussion. But that's one set of challenges I'm not going to go into a whole lot of depth about. But since I've been here looking at and learning about some of the projects that you have underway, I've learned a little bit about what some of your challenges are. And obviously you have a fragile architecture in terms of your utility supply system. You're at the end of a pretty long transmission line. And if that goes down, then not only Jefferson County, but a lot of other parts of the peninsula are down. That's an issue, obviously. Another issue, and I view it as a challenge even though it's actually a blessing, is that you have cheap electricity comparatively. That's a problem because if you want to come up with an alternative, you need an alternative that's not going to be too much more expensive than that cheap electricity. That's easier to do in New York than it is here. The projects that we've been working on there actually will compete just directly on a price basis against retail electricity. That's going to be tough to do in Washington, anywhere really in Washington, but here as much as any place, and maybe more so because of the constraints you have on fuel supply. That's another issue down at the bottom here. Fuel costs are high, relatively speaking, and delivery is constrained. If you had a cheap natural gas supply, it'd be easier to put a microgrid in. The microgrids we're developing in New York and in Maryland both rely on natural gas. And one thing I wanted to say is that a microgrid is only as resilient as your natural gas supply. So, I'm sorry, not natural gas, as your fuel supply. If there's an interruption in your fuel supply, then it's just as out as as the power line is out. So in a place like Jefferson County, that means storage. You need to store as much fuel as you need in order to meet your resiliency objectives. And what I mean by resiliency objectives is how long do you need to be able to operate that microgrid during an outage? Do you need it just for an hour? Do you need it for a day or 2 weeks or indefinitely? If it's indefinitely, you're going to have a tough time because you can't rely on natural gas coming in on a pipeline. Where there's natural gas coming in, we think of that as, and in fact it is, much more resilient than the electric system. It's really rare that natural gas pipelines go down. It does happen, but very rarely. So that's adequate in those locations. Here, you just need as much storage as possible or the means to produce fuel or source it locally. And that would mean biofuels or some other source. People are talking about ammonia production by cracking water and creating hydrogen. Something like that is necessary in order to attain long-term resilience. But that all depends on what your objectives are. If you can live with a week's worth of resilience, then you just need a week's worth of propane storage, and that's the end of the discussion. Or you need batteries that can store as much PV, not as much solar energy as you're going to need for ongoing operation. One thing I wanted to mention too, dispersed population and dispersed critical facilities. It would be easier, it's always easier if the critical facilities and the loads are located close together, and if they're large. The more loads you have and the more diverse the loads, the easier it is to build a microgrid to serve them. if all of your loads peak at a certain time of day, and then they drop off completely at another time of day, and if your thermal load goes like this and then it's way down, it makes it really more difficult to design a cost-effective energy system. But if you have diverse loads where some are peaking at different times of day, and especially if you have a thermal load, depending on your scenario, typically we say if you have a thermal load that's consistent over the course of the year, that makes it easier to develop a cost-effective energy system. What we see here is the population is dispersed, the critical facilities are very dispersed, and so it's going to require a number of smaller solutions, and it's going to require solutions that can meet changes, that aren't mitigated by diversity of the loads. And that's all I'm going to say about that, so I don't go too far into the weeds. I think there are some clear opportunities here as well, and first of all, microgrid technology is an opportunity because it can meet your resilience needs. The technologies that are evolving, not just the ones that we're working on, but that a number of different companies are working on, make it possible to make better and better use of the resources that you do have available. Just a couple of years ago, the capabilities of the control technology wasn't as good as it is today, and a couple of years from now, it's going to be better yet and more cost effective. So that's an opportunity that's bodes in your favor. I use the terms here scalable and flexible. That's been a challenge for microgrid control technologies for a number of years. Scalability refers to its ability to cost effectively serve a big microgrid or a very small microgrid. Most of the technologies in the past have been really expensive, really only useful for very large, comparatively large microgrids. And now they're becoming more cost effective to serve smaller and smaller microgrids. The ones that we're working on in New York, for example, would be relying on off-the-shelf computer hardware, hardened computer hardware, and software solutions as opposed to really large-scale utility-grade solutions that are very expensive and really great, but way overpriced to serve a tiny nanogrid kind of scenario. Those solutions are available, or becoming more available as we go on. One thing I wanted to mention is that you have communities throughout the Olympic Peninsula, of course, especially in Jefferson County and Bainbridge Island for that matter, that have similar problems. And so if you can work together to try and solve those problems, then you're going to be in a better position to come up with cost-effective and technically viable solutions. It's a matter of economy of scale. Even though we're talking about small systems, it still makes sense to try and band together, band your buying power together and bring the same brain trust or the brain power together to design solutions that will work throughout the area. If you try to go alone, just one community, it'll be less cost effective and more difficult than it would be if you're able to band together as a region. So I would view that as an opportunity, although I'm sure it has its share of challenges as well. There's untapped potential. I mean, this is true everywhere. There's always untapped efficiency potential. And what that means really is that to the degree that you can look at your existing systems and try to figure out how to use energy more wisely and just simply use less energy, that means a microgrid or any other community energy system can be more cost effective because you don't have to build as much supply or use as much fuel to serve it. So I view that as an opportunity as well to try and, first of all, reduce your amount of energy usage, and second, make it more possible to have a cost-effective community microgrid to serve those loads. And then finally, I wanted to mention that anything that you can do to invest in local energy assets and local energy resource utilization is going to bring economic benefits to the community. One way of thinking about it is, an energy dollar spent on a number of kilowatts goes out of your pocket, but where does it go from there? It either goes up a power line to some other state and to investors, or to BPA, I guess in this case, Or if it goes into systems that are generating power locally, then it goes into the pockets of the owners of those systems. And if they are local people, then they put it back into the economy locally. So in other words, a microgrid and a community energy investment generally will overall improve your local economy because energy dollars spent are going to be retained in the local community. And that's a really substantial opportunity for communities really all across the country. And something that's a little bit difficult to quantify, honestly, but to the degree that local resources are owned locally, then the money that flows to them will be retained locally more than it would be if it were paying for power supplies from some power plant 2 states away. So looking at the clock, I'm almost out of time and a little gone further than I really anticipated, so I'm going to jump through really quickly here. Just a couple of things to explain what it is that we do at Microgrid Institute. So I mentioned the projects that we're working on. We're the prime contractor on all 3 of those projects. We are leading multidisciplinary teams that are working on a wide variety of activities, including technical design, laboratory testing, but additionally looking at regulatory and financial options and challenges. So we are a multidisciplinary collaborative teaming organization. That's really what we are all about. One of the key things that we provide as a service is feasibility assessment. So we usually take a 2-step approach or 2-phase approach to assessing the feasibility of a microgrid. And first is essentially a screening process, taking a fairly quick look to get a sense of whether there is a path that we can see forward for a microgrid in that scenario. And if there is, then we can move on to the second step, which we consider an iterative process. And what I mean by iterative is that we don't just look at one option and say, is that a thumbs up or thumbs down answer? Instead, what we do is say, what are the objectives, what are the needs, what are all the options, then try to decide what are the most logical options, and then try to determine which of those are the most feasible. So that we can come out the other end of that iterative process with recommendations, basically saying, here's an approach, this is the expected economic cost benefit, and here's how we think it can actually be deployed. So that's the approach that we take to feasibility assessment. The first step is pretty small scale and relatively inexpensive. The second step is larger scale and more expensive than maybe a really simple feasibility assessment, but the result is a lot more in-depth and provides recommendations that you might not get otherwise if you took a more simple approach that just said, does this system work or not? We say, we're going to try and figure out how a system will work. And it's a kind of early stage development is what it really is. One thing I wanted to mention, we strongly encourage and we work closely with communities to try and help maintain a focus on integrated planning, as I mentioned before. So there are lots of different options, and it can be very easy to get lost in the woods, or lose sight of the forest for the trees, as it's stated. But we're focused on that integrated planning approach, in particular because we think, and what we found, is that microgrid development can serve as a stepping stone or a platform for development of many other types of energy resources that can bring additional value and savings to the community. And this pyramid tries to sort of exemplify that the resilient energy microgrid is sort of the tip of the iceberg, that in fact some of your best savings and potential for reducing emissions is actually found in something like district heating and in clean transportation for that matter. But that development of a microgrid can serve as kind of a hub to lead toward the development of those things. If you don't do it that way and you work on those things in isolation, you can run into the kinds of conflicts that I mentioned before, where you kind of wind up shooting yourself in the foot. If you go too far down a certain path, it may be too late to use the investment that you put into that to serve the resilience needs of the community. So it's a good idea to take an integrated approach, and it's a good idea to focus on the mission critical needs for energy first, because those are the things that you're going to need the most during an outage scenario. If there is a tsunami or an earthquake or wildfire or whatever, what you're really going to be worried about is your critical services. So start there and look at what are the solutions for your critical assets, and then other planning can flow naturally from that. One of the other things that we do, I'm a communications professional, actually. I spent a lot of my early part of my career, 2/3 of my career, as a journalist. And we focus on community engagement and outreach and trying to convey the messages that are necessary to support the community's objectives. So that's one way that Microgrid Institute can help to help a community maintain focus on those objectives, is providing community engagement and outreach services. And that's been valuable, especially in the New York communities that we've been working with that have so many different stakeholders involved. Keeping them all moving in the same direction is a pretty important challenge, and it requires somebody who isn't necessarily in the local political environment, somebody who can come in objectively and say, here's what our objectives are as a community, let's keep moving in that direction. I think I went over this, and I want to leave enough time for Q&A. So I think I'll leave it at that. This is a list of kind of how we get started with most of our clients. We have some threshold questions that we like to ask. And the key one is, what are your objectives? And that's something that I think would be very useful to have ongoing conversations with many of the stakeholders in the community. That comes to the end of my prepared presentation. I'm delighted to have an ongoing discussion here. Thank you.
Great, thanks for a great presentation. One question, you mentioned a school that had a solar array and said that it'd be tough sort of after the fact to include that. I guess I'm curious why you couldn't, sort of put some switches or other things sort of in between it and the system to make that.
Right. In both of the New York projects that we're working on, we ran into that problem, actually. And we looked really carefully at trying to do exactly what you said. In one case, I mean, it's kind of baffling to me, actually, the outcome. The solar array was just right down the road from the high school, and the high school was one part of one of the microgrid zones that we had planned that had some clinics nearby and a water facility. The cost of trying to connect that array to the rest of the microgrid was on the order of $1.5 million, even though it was less than a mile. Because it's really expensive to bury cable. And if you rely on above ground cable, then that's not a resilient resource. And we did look at trying to use the above ground resource, but at the end of the day, the complexity of trying to do that made it really too difficult. That's the technical perspective on it. The more complex and also really frustrating perspective on it is that what happens when a school district or any entity signs up with a remote net metered, that's what it's called, remote or virtual net metered facility like a solar array. What they're doing is they are dedicating their, and in this case, 100% of their electricity purchases, they're dedicating all of that to purchasing power from that solar facility. When they do that, what that means is we can't come in and build something else to meet their resilient power needs because they're already buying all of their electricity from somebody else. In this case, from the utility. They buy it from the utility and then sell back, in effect, the power from the solar array, right? So they have to buy all their power from the utility. They wouldn't be able to buy it from the microgrid. Now, in the PUD, maybe there's a solution that would work. But in this case, it wouldn't work. I can talk a lot further about it and get more frustrated, but I don't want to do that. So it's a perverse outcome, honestly, that here's this really great high value asset that's useless in an outage. I'm sort of furious about it. It'd be like spending $50,000 on a PV system on my rooftop and then not being able to use it during an outage. How sick is that? But that's the case. I mean, that's pretty much the case everywhere, that people put a lot of money into rooftop PV and they can't use it during an outage. That's what we're dealing with on a community-wide basis. That's unacceptable. That's what I say. Close the door on that.
What was very defining for me at the beginning of your conversation here is the fact that the microgrid is really catering to the individuality of the needs of people instead of the grid that we are used to, that was more in tune with the industrial evolution, probably. So my question to you, out of curiosity, basically, is it possible to go so micro that each property could have their own system?
Yes, and that future is out there. I mean, we tend to think of that as a nanogrid future. And there's ongoing discussion about that. At some point, there's sort of there's a day over the horizon where solar plus storage, and that's what people tend to think about it also, solar plus storage becomes generally competitive across the country, and that's a game changer for the entire electricity system. Until then, it is a matter of incremental improvements in cost effectiveness, and those improvements start out with larger scale systems and get increasingly cost effective for smaller and smaller scale systems as we go on. I guess in a way what you asked is a yes-no question, and the answer is yes, but I don't know when. The more complex answer is we're kind of slowly getting there, and depending on where you are in the country, you might already be there. In Hawaii, for example, electric rates are so high that a battery and storage system, or a battery and solar system, can already be cost effective in some places. So yeah, we're getting there. The problem I mentioned before is that the smaller the system is, the more complicated or more difficult it is to maintain balance. So that's one thing to keep in mind. That's certainly true in the case of a home energy system. Ultimately, in that case, what you really have to have is a solar and a battery, especially a battery that's really oversized. I would think about it in terms of oversizing it, because it has to have a lot of capacity to quickly adapt to spikes in demand. So if your freezer suddenly turns on, when that pump starts up, that's a big spike in demand. And if you have a system that isn't scaled to do that, it won't be able to handle it. I don't want to talk too long about that question, but I mentioned that how the control technology is getting better and better all the time. I foresee a day when the control technology will be powerful enough and the systems will be cheap enough so that the control system can say, okay, fridge, freezer, don't turn on, and because the fridge is running or the dryer is running or whatever, and then wait for that cycle to end and then it can turn the freezer on. We're trying to do that on a building scale at this point. You're signaling a building energy management system to say, okay, for now you got to keep below threshold A, right? It's one thing to tell a building energy management system to do that. It's another thing, cost effectively, to have a home that's capable of doing that. It takes a lot of automation that's kind of expensive at this point. So that's a long answer to your question, but I guess what I wanted to get at is for now it means oversized batteries. At some point in the future, maybe it means a smarter, cheaper control system than we have today.
Thank you. Excellent. Who else has a question?
Yeah, I don't see why you were so hard on grid-tied solar systems. The problem is the inverter on these systems, and that's maybe 20% of the cost. And you can replace the inverter with an inverter that will provide power. And in fact, many of the newer inverters for grid-tied solar have a plug on them. You can plug in and get power out of it in emergencies.
Right.
They're designed that way, and so it's not that hard to fix it.
No, you're right. It just takes investment. That's true. Absolutely. But most systems aren't being financed that way. Most systems, it's all about a zero-sum game, kind of. Whoever can supply the cheapest system is the one that's going to sell the most in a given market area. And so they've been financing and developing and rolling out solar systems that are as cheap as possible. And they do offer that. I mean, many solar providers offer that as an option, but it's more expensive, so you don't see a lot of it being deployed. There is a percentage of it that has been deployed, and people can convert. You are absolutely correct about that. They can convert systems, but it's a whole lot better if you design it from the beginning to be an islanding system.
Thank you for the presentation. I just have a quick question. I'm totally unclear on this, and I guess I come from it with a lovely relationship like Boulder has with Excel. You know, utilities don't want to give up market share, so explain to me how you get these behemoths to, you know, allow microgrids in and how that relates, if you can do that in a short period of time.
It's a 1:28. We have 2 minutes, and you asked a very, very complicated question that I don't think anybody has a really good answer to. Yeah, that's a question that's keeping an awful lot of people up at night in the utility industry. I think that part of the answer is to wait and see what happens in New York and to see how California proceeds over the next few years with some of the initiatives they have underway, and how the utilities respond to those things. That might shed some light on it. New York is really a good crucible right now because they're specifically trying to answer that question. They're actually saying, you know, what is the system going to look like? What's the new role for the utility? So that this death spiral argument doesn't keep coming back up, you know, where the utility is saying, we're losing more load, and so the fixed costs per person are going up, and at some point we can't maintain that anymore. It's a little bit of a spurious argument, but you know, it's not completely without any merit, and it's causing utilities not to want to, or it's giving them, you know, pretty strong ammunition to avoid really radical restructuring in the market. What New York has been proposing is, I'm not sure I'd call it radical, but I think it is a step in the right direction where it's helping utilities to think about their role as a platform provider, and as sort of like the Apple Store for the energy market in a way. So that lots of people can access that market to sell product and buy the product that they want, but the utility is there making sure that the overall system you know, maintains reliability and that it's there as a conduit for those kinds of products. That's what New York envisions as the utility's role, and evolving more in that direction as time goes on. And we'll see how utilities respond to it. I certainly don't have a slam dunk answer for you. I don't think there is one. I think this is a market that evolved over the course of more than a century around a certain architecture that was based on the cost effectiveness and the you know, scale economics of a central station generating model. And it's going to take a lot of time for that to evolve into something that really is better accommodating of the newer technologies that are coming out. I know it's not a satisfactory answer, but it's the truth as far as I can tell. There's no easy path. Okay, thank you very much. I've really appreciated the opportunity.